All right, here's a new problem we're going to work. We're going to use conjugate beam again for this one. Now, it wants the slope and displacement at the midpoint of the structure. Okay? So just like our previous problems, our first step is to draw a shear moment diagram. So I'm going to go over here at A and assume positive shear at A, and go over here at B and assume positive shear at B. And I'm going to solve for those values. So I'll start by summing moments. And I'll just decide to sum moments at B. Why not? So summing moments at B, this applied 5 kip load creates what kind of moment? Mr. Van Tilburg. About B.
At B?
About B, this force.
Positive.
Excellent. And that has a moment arm of 3 feet. And then the reaction over here, which is the shear at A, is what kind of moment? Negative. And that has a moment arm of 12. So it looks like the shear at A is 1.25. And that would be units of kips. And then we can quickly sum forces in the y direction. And that would be the shear at A is up, the shear at B is down, and then the 5 kip force is down. So we can solve for the shear at B, and it looks like it's going to be minus 3.75 kips. Does that work out? Okay, not surprising. You would expect with this kind of loading that the force would be up and the force here would be up, which is negative shear. Okay, now we can come back over here and draw the shear force and bending moment diagram. So there's my limits of the problem. I know something's going to happen there about the force, so I'll add that to my template also. And then I can construct the diagram. There's the positive x value, there's the positive shear, and we'll do this in kips. So what is the shear at A? 1.25, and it's positive. The change in shear over the first 9 feet is the area of the load diagram, which is 0. So unchanged. The slope of the shear diagram is the load. The load is 0. So we have a 0 slope. So a constant shear over the first 9 feet. That's not unexpected. And then as we go from the left side to the right side, how much does the shear change? 5 kips. And it's negative. So 1.25 minus 5, negative 3.75. I know the change is 0 because there's no load, and it matches the shear that we had calculated. So that all looks pretty good. So what should the what should the moment diagram look like? Well, let's draw it.
Kind of like a triangle.
Kind of like a triangle. I like that.
Isosceles triangle.
Isosceles? I don't know about that.
Scalene. Yeah, scalene. That one.
Baleen, like a whale's mouth? Baleen triangle?
Yeah.
All right, so we do know the moment somewhere. What's the moment at A? 0. So we know we're starting. What's the moment at B? 0. We know where we're ending. So the change in moment over the first 9 feet would be the area under the shear diagram for the first 9 feet, which would be 9 times 1.25, which is 11.25. And of course we know the slope is the value of the shear, and the shear is constant and positive, so we have a constant positive slope. The change in moment over the last 3 feet is the area of the shear diagram, which is negative 11.25. Brings it 0. That's great. And we know the slope of this curve is constant and negative. So there is our moment diagram. So now I'm going to draw my conjugate beam, and I'm going to put this on it as load. So looking at your support conditions, you'll know that they're both external pins and rollers, and how do those map into conjugate beam? They are unchanged. So you're going to come back with a pin and a roller. And I'm going to pick this thing up. I'm going to plop it right there on top of my my beam, because that's what my moment diagram looks like. I'm just going to stick it right on top. And now I'm going to look at this and I'm going to say, what kind of moment is this? Positive or negative?
Positive.
It's positive. So that means it's going to be a positive force. And positive forces are up. And that peak value there is going to be 11.25 kip feet. That's the moment. And now we have to divide it by E and I. This is 9 feet. This is 3 feet. Okay, now before we go too much farther, let's think about a strategy for how to attack this problem. Go back to the top and it says, hey, I want the slope and displacement where?
The
Midpoint. Right here in the middle at 6 feet. That's going to end up being about right there. Do you want to work the right side or, the left side or the right side? Right side to me looks like a big problem. You got a triangular area and then you'll have a trapezoidal segment. I don't like that. I think the left side looks a lot better off. So really all I need is the left side shear. So what I'm going to do right now is go ahead and assume that I do have a positive shear at A and one at B, even though I'm not going to compute it. And now I got to find that. To find that, I need to resolve all these forces. So I'm going to need first to handle this force, which I'll call F1, and I didn't give myself a lot of room here, but I'll stick this one here and I'll call that F2. So I got to first calculate those two forces. Let's start with F1. It's a triangle, so I know it's 1/2 the base, which is 9 feet, times the height, which is 11.25 kip feet, divided by EI. F2 is also a triangle, so again it's 1/2 base times height, and that's 3 feet. And they share that same height, 11.25 kip feet divided by EI. I don't know if I can squeeze them in there or not. I think I'll just hold on to those for a second. I'm going to sum moments about B to find A. So I'm going to want first the distance, I'll call it D2, and then the distance, I'll call it D1. So what is D2? The distance from B to the centroid of this triangle.
2.
Yeah, it's 2/3 of 3. That will be 2 feet. And then D1 is going to be what? Well, it's going to be 3 to get there, and then how much of 9? 1/3. So I'll have 3 plus 1/3 of 9 feet, which is 6 feet. So I get all the pieces I need. So let's do that. So I will sum moments about B. Now when I sum moments about B, both these forces, what kind of moment are they going to create about B? Positive or negative? With right-hand rule. Negative. So now, somebody tell me, what is the value of F1?
50.63 over EI.
50.63, and that's kip feet squared over EI. That's F1, right? And that's times D1, which is 6 feet. And then what's F2? 16.88? Yes? 16.88 kip feet squared divided by EI. And that moment arm for F2 is 2. And then I got the shear at A, which is going to create negative moment. And it has a moment arm of 12. So what is the shear at A? It's going to be negative. $28.2. I have no idea.
28.1.
Oh! And that will be kip feet squared. Now this is just an intermediate value, but what is that? What does that tell us about anything in the real beam, the original beam? What is the shear at A? How does that map back to the real beam? Slope at A. So that's the slope at A. Would the slope be negative? I think so. If you look at the way this beam will deflect, I have a feeling it'll deflect. Oops. I have a feeling it'll deflect something like this. So you do have a negative slope at A and probably a positive slope at B. So now what do we do? Well, now I'm actually going to come back and cut the structure at the place I want to know the shear force and bending moment, which is given by where I want the slope and displacement in the real beam, which is right in the middle. And I'm going to look at the left-hand side. So here's going to be my free body diagram for this chunk of the beam. So there it is. I'm going to put that value on it. So I assume the shear A was acting up. It's negative, so it's actually down. And that would be 28 point... What was this? What was it? 1? Kip feet squared over EI. I'm cutting it in the middle, so this dimension is 6 feet. I do want to know the shear and the bending moment at those points. So there's my positive shear force and bending moment. And then I've got this distributed load, and it's acting up. First thing I have to figure out is what's the intensity of the load here. I know at 9 feet it's 11.25. What is it at 6 feet? It should be 2/3 of that. I think 2/3 of that is 7 something? 7.5? Is that right?
Yep.
So that's going to be 7.5 kip feet. Oh, just kip feet divided by EI. So now to solve this problem, I need to resolve that. So I'm going to come back and compute another force. I'll call this one F3. And that will be the area of that curve, which is 1/2 base, 6 feet, times height, which is 7.5 kip feet divided by EI. What's that?
22.5 over EI.
22.5, and that will be kip feet squared over EI.
We solved for F3.
I didn't write that in there, did I? F3 equals. And then also I want that distance, D3, but that's just going to be 1/3 the distance. 1/3 of 6 is 2. Okay? So now let's sum the moments. So now I'll sum the moments at this cut and make sure it's in equilibrium. And what do I get? Well, starting here, This moment with my sign convention is positive. The moment about the cut produced by F3 is negative. So that would be negative 22.5 kip feet squared over EI. That's the force. And the distance, 2 feet. And then I have my reaction force out here, which is creating positive moment. And that's 28.1 kip feet squared over EI. And that has a moment arm of 6. So it looks like the moment is going to be negative. And what is it?
Negative 123.6.
123.6? Anybody else get that? Yes? 123.6, and that's going to be kip feet cubed over EI. Negative is a good sign because I know the displacement here, that point at the midpoint is going down, so negative is good. I've kind of run out of space. I need another. Anybody got a piece of blank white paper?
Oh, that I do.
Oh, you do? Excellent. Why do you carry blank white paper?
I like to do my homework. I'll hand it to you. I mean, for some reason.
All right. So I'll try to do this. I'll keep that so you can see it temporarily. And we'll now come back and do what here? Sum forces. So I'll come up here. And we will sum forces in the y direction. So we can find our shear value. So looking at the diagram, the shear is acting down. My F3 force is up, and that was 22.5 kip feet squared divided by EI. And what else? I've got the 28.1 force acting down. So what is the shear?
Negative 5.6 kip feet squared over EI.
That's pretty small. 5.6. Now what does that mean that the slope is negative? That means you're still on the part it's going down. It has not gone through 0 and then started back up positive. So that means we probably have not found the maximum displacement yet. We're getting pretty close because when you take 5.6 and divide it by EI, it's going to be really small. In fact, that's what we're going to do next. So let me pull this back out, and let's remember that the moment maps back to the displacement, and that would give us a value of 123.6, and that's kip feet cubed. Now we're going to divide by E and I. E was 30,000 KSI, and I was 800 inches to the fourth. So we've talked about before, the kips cancel. This cancels and makes that squared. So I have feet cubed over inches squared. So I'm going to end up with the dimension of length, which is good. But I want to convert that cubic feet to cubic inches. So that'll be 1,728 inches cubed. And what is that calculation?
0.009.
0.009. That's pretty small. We're getting pretty close to basically not moving this thing at all. Now, if you look back, it's only a 12-foot beam. This room is about 24 feet wide. This beam would only be about half the distance of this room. 5,000 pounds sounds like a lot, but on a chunk of steel with a moment of inertia of 800 inches to the fourth, that's a pretty stout little short beam. So I probably should have upped the load a little bit on that to make it a little more reasonable. It doesn't really matter. We talked about this from a design perspective, and this is something that you guys can think about too as you move forward. You're not going to be able to change the E of your chipboard. You're not going to probably be able to change the moment diagram. It's fixed, but you can change that. And you can change that by changing shape. So you really want to maximize your I while minimizing your weight and cost. And to finish this off, the shear maps to the slope, which we've computed as 5.6 kip feet squared divided by EI. And when we do that conversion, we still divide by E, which is 30,000 KSI, and we divide by I, which is pretty big. So now kips cancel, inch squared, this becomes 2. We got square feet over square inches, so we're going to come out dimensionless, which is good, but 1 square foot is 144 square inches. So what's that equal to?
Negative 3.36 times 10 to the negative fifth.
3.36 times 10 to the minus 5?
Yep.
That's a pretty small angle. Getting pretty close to 0. Again, you can see it takes a lot of time, especially when you're under a time crunch in exams. So I would prepare myself to do it, but not be required. Maybe it's as a bonus. So any other questions about this one? Okay.